Hey, welcome to another seminar here. We have a couple more left. We don't have a seminar next week. There's a class here, and I think we have one more after that. Two more. Tricia's here. So today we have Alex Brand speak on his master's thesis, actually. So this is about 2 years worth of work on using wrap in concrete. So if the asphalt people don't use all the wrap, we may have an application here for them. Alex got his undergrad here in, let's see, 2010.
Yes.
And so he has officially been approved with his thesis today, I think.
Yep.
The thesis
morning.
office. So he's, well, I wouldn't say he's done, but he can at least graduate.
Graduate the master's at least.
Anyway, welcome, Alex.
All right, everyone, thank you for coming today. I'll be, like I said, presenting on what my master's thesis was, which was on the use of fractionated reclaimed asphalt pavement, or FRAP, as a replacement of coarse aggregate only in concrete that's composed of 3 cementitious products, so it's ternary, and I'll get more into that. First of all, I'd like to thank Professor Raisler, who was my advisor for this project. Also Professor Alcati, who was also on the project. The project was funded by the Illinois Tollway, so thanks to them and Steve Gillen. Also thanks to Peng Chang for running the asphalt-related tests. He ran the asphalt content and characterization and the dynamic modulus test for this. And a few other thanks to CTL Group, state testing, and our materials providers. So why do we need to use FRAP in concrete? First of all, there's a high disposal cost for any wrap or FRAP for that matter. So there's great economy and reducing the carbon footprint by using these recycled materials. And the reason why the tollway has so much FRAP is that in the past few years they've been milling up their old overlays, their old pavements, and then fractionating them. So they have a number 4 sieve screen to separate coarse from fine. And then they also have a coarser screen at the 1/2 or 5/8 inch scale, and they get rid of everything above that. So all the coarse FRAP they have is between the 1/2 and number 4, essentially. Everything passing the number 4 they've been using in their new overlays in conjunction with reclaimed asphalt shingles. So now they have these large stockpiles of coarse FRAP and nothing to do with them. So they gave us money to look at and putting it into concrete. Now wrap has been used in concrete before. There's been a handful of studies, maybe 20. Biggest thing being the Austrians started using it back in the 90s as part of a 2-lift pavement. So in the bottom lift, they have probably 7 inches or so of recycled aggregate concrete, and they top that off with a thinner, maybe 1 to 2 inch of virgin concrete. And that's something that they've been using since the 90s. Their current standard does permit it up to 20% in the bottom lift. They usually use only 10%. But they've been using it for years, mainly just that they crush up the old roadway with the overlay on it. So they have recycled concrete and some wrap in there, and they use that in the bottom lift. There was also a 2-lift study done in Kansas in the late 90s where they did 15% in the bottom lift, same as the Austrians, just the bottom lift, top lift was a virgin concrete. When they tested this a few years ago, the pavement still had pretty good load transfer efficiency at 85%, which is pretty good. And you could see that the faulting was maybe a little bit higher than the control, and also a little bit more spalling than the control. Although, however, their control is just a full depth virgin concrete. It wasn't a 2-lift, virgin on virgin. The Tollway also did a test project 2 years ago in October, and what they did is they replaced an on-ramp, and they did a composite pavement this time. So they did, what did they do? I think it was 7 inches of concrete with 30% wrap, and then they topped that off with 3 inches of an asphalt pavement, so just a composite pavement. And pavement's still going pretty good, and they have another test project coming up this summer, which will be very exciting. So looking at the literature, like I said, there's maybe been a handful, 20 or so studies on wrap and concrete. For the most part, you'll have reductions in strength and modulus, which are kind of the big important parts we need to look at. A lot of the other properties kind of have been variable with the workability, the air content. One study would say it increased, another says decreased, so it's variable depending on the wrap source used and how they made it. But some other important things, you know, shock absorbent properties were found to increase, so kind of fracture resistance, which is good. And then just some other handful of studies looked at some other things like permeability, which they found to increase. So now getting into what my project was here at U of I. Mix design. So like I said, this was a ternary mixed concrete, which consisted of 65% cement, your normal Portland cement. Then there was 25% ground granulated blast furnace slag. That's just a byproduct of steel production that's used commonly in concrete. Another thing was it was 10% fly ash, which is from coal burning. And both of those products are commonly used in concrete. Usually you only replace with one of those. Ternary mixes are, I shouldn't say new, but they're gaining more ground in terms of use. So the tollway is definitely interested in using high proportions of sustainable materials because slag and fly ash, both being byproducts, are sustainable materials. Now the cementitious content we used was 630, which is a little bit high for a regular pavement. Usually a pavement will have maybe 575 pounds per cubic yard, but we wanted to have enough cementitious content to have good strength gain since we knew the strength properties would probably be decreasing. Water to cement ratio was 0.37. Again, a little bit low compared to a normal pavement of say 0.4, 0.42. And then the real important thing, we looked at replacements of 20, 35, and 50% of just the coarse aggregate with FRAP. And then also we used some chemical mixtures to get good workability and air entrainment. There's just the mix design if anyone's interested. So now the fresh properties, the workability of fresh concrete. Pretty much what we found is that the slump increased with our increasing FRAP content. Interesting thing about that is we reduced the water reducer dosage as we increase the FRAP content. So typically with a normal mix, if you reduce water reducer content, your slump should go down. So we had an increase in slump despite reducing water reducer. So that was an interesting find. Unit weight also decreased, which is not surprising since there's an asphalt layer on that aggregate, which has a lower specific gravity, so of course the unit weight will go down. Air content pretty much was variable. This is just for one of the mixes I did. Usually it ranged in about 6.5% to 8% typically, and that was a constant air entrainer dosage I used. So a little bit variability in the air due to the FRAP, but relatively I would say it was just unaffected. So now looking at the compressive strength, we have our 0, 35, 0, 20, 35, and 50 going down. And as you can see, at our ages, our strength goes up with age, as expected, but at each age, there's a reduction in strength due to the FRAP content. What's important to note here is the IDOT strength requirement, which requires 3,500 PSI at 14 days. For the most part, these mixes pass. The 50% was just below that limit. It was 0.3% below that limit, but with other mixes we got it above 3,500. So that's important to note is we need to meet IDOT strength requirements. Split tensile strength was a similar behavior with reduction in strength with increasing FRAP. Similar with the flexural strength. Again, we have just reductions. Not sure why we had a higher 35% there. It was interesting behavior that we were not expecting. But what to note here is IDOT has a flexural strength requirement of 650 PSI at 14 days. Now that is for center point loading. What we did is called third points. You're loaded at every 1/3 the span. So you have 4 points essentially. 1, 2, 3, and 4. For center point, you remove one of these top ones and put it in the middle. Center point will have a higher flexural strength, but higher variability as well. This setup, you'll have a constant moment in between the span where it'll fracture. So that's why we did third point testing instead. But if you assume the typical difference in center point versus third point loading of 15%, we can see that about 570 psi is what IDOT would say. They don't have a spec on third point, but we're just assuming here. So pretty much we could pass the IDOT spec for flexural strength, most likely. So now looking at concrete shrinkage. This test, we have a beam with gauge studs in the end, and we have it in a humidity-controlled room at 50% relative humidity. So at that humidity, you'll lose moisture, your concrete will shrink. So it's an important property to know in the real world, so you avoid shrinkage cracks, things like that. For the most part, our shrinkage, we concluded, was unaffected by the FRAP. 35% was a little bit lower here, but you can see the 50, 20, and 0% FRAP mixes were all about the same shrinkage rate after 90 days. Concrete age, the concrete was cured for 28 days before we put it in the shrinkage room. We also tested it immediately after casting. So you'd cast the concrete, a day later you'd put the concrete in the shrinkage room, and we found similar effects by testing it at that age as well. Also with the shrinkage, you measure the mass loss. So every time you go to measure the shrinkage, you just weigh the beam and determine how much mass you're losing. And we found a slightly greater mass loss with the higher FRAP contents. Another shrinkage test we did is known as restrained ring shrinkage. With this test, you have an inner steel mold that's ½ an inch thick, and you have strain gauges attached to the inside of that steel ring. And then you have 3 inches of concrete cast around that steel ring. You seal the top, the bottom is sealed, so all your drying is on the outside circumference. So as the concrete dries, it shrinks, and you get strains on that steel ring. Eventually, the test should tell you at some point the concrete strains will get so high that the concrete will crack. And that's pretty much what this test is looking for. You're measuring the strains, looking for when it will crack. Problem with this test is that our rings did not crack. So pretty much the only data we could get from this test was the shrinkage strains. You see a bump here. A bump usually means a crack. In this case, there was a malfunction in the shrinkage room, and the temperature went down and resulted in a few of our data had spikes like this, but there was no cracking, pretty much just a spike due to that. And you can see if we ignore that spike, the strains went on the same rate, as you can see. So pretty much after 90 days or so, we stopped the test after no cracking. We could see that the 50% mix had lower strains than the 0. And so then the other thing we tried is a plain cement mix. So we have the red and the blue were our typical mixes with ternary blend concrete. This green one now, we got rid of the slag and fly ash and just did plain cement, figuring that should then crack, as typical mixes do when it's just plain cement. However, still no cracking. So again, pretty much all we can gain from this test is that we have a greater stress relaxation with FRAP, which could lead to higher creep characteristics, which is another test we'll be running probably in the next year or so, but we haven't run yet. The 0 FRAP mixes did also have some stress relaxation, but not nearly to the magnitude that the FRAP mix did. I meant to take that one out and do this one instead. So rapid chloride penetration test pretty much is a test that we use to give us an idea of the permeability or diffusivity of the concrete. So if you have very interconnected pores in your concrete, you'll have high penetrability of chloride ions. So with this test, on one side you have a 2-inch thick concrete disc. On one side you have a sodium chloride salt solution. On the other side you have sodium hydroxide. And then you apply a voltage across the two cells, and you'll drive the chloride ions through. And pretty much we have a test set up. You have a machine that will measure the charge passed over a 6-hour testing. And pretty much what we get from that is from these ratings, the average is all about around 1,000 for each of our FRAP contents. And that correlates to a rating of low to very low permeability, is typically what people say, or penetrability, if you will. Just in terms of this test, if you have a concrete that's more on the scale of 2,000 to 4,000, you have a higher permeability concrete. So this concrete at 56 days has a low to very low permeability, which is very good for us. And that's probably mainly due to the slag and fly ash we used. If it was plain cement, these ratings would probably be higher. We also did freeze-thaw durability. So with this, you have prisms again, and you subject it to freezing and thawing cycles underwater. You have a prism in this chamber that goes down to 0 degrees Celsius and then goes up to 40 degrees Celsius and just alternates between those cycles, and we measure it intermediately every 36 cycles or so. So the test is ended at 300 cycles, and our relative dynamic modulus you measure was pretty good. All the mixes, the lowest was the 50% FRAP at 86%. Usually if you look at patching mixes will specify a durability factor of, say, 80%. This test actually ends at 60%. So in reality, we have pretty good freeze-thaw durability, and that's mainly due to the air entrainment we use. We have enough entrained air voids that our freeze-thaw resistance was pretty good. And just here's the freeze-thaw durability over time. You can see that our 50% mix here at the bottom eventually had the lowest durability, but still pretty good. And you can see that the 20 and 0 were both pretty good. Now looking at elastic modulus, this is just a test setup. We apply a compressive strain. You measure with an extensometer, the stress versus strain essentially. And as consistent with the literature, we had a reduction in elastic modulus with increasing FRAP. Similarly, dynamic modulus, we have 0 to 50. We have a reduction in dynamic modulus. This test, we adopted the hot mix asphalt dynamic modulus test you guys do. We took a normal 4x8 cylinder, cut 1 inch off the top and bottom, so it was the 4x6 typical specimen size, and then tested at dynamic modulus. For the most part, we found that it was frequency independent. There really wasn't much change with frequency, and similar with temperature. We tested at 4, 21, and 54 degrees Celsius. There really wasn't much temperature dependency either. The important thing to note that is just the dynamic modulus decreases with FRAP content. Similarly, from that test, we have the phase angle we measure, so 0 up to 50. We can see that because it was concrete, it's a pretty low phase angle, indicating it's an elastic material. But as you add FRAP, you have slightly greater viscoelastic properties, but really, with a degree change of, say, 1 degree, it's not very significant. Just comparing dynamic to elastic, typically dynamic modulus will be a higher value, which for the most part, that's what we saw, except for the 50% mix, we saw a higher elastic modulus versus dynamic. Now, this is a test, another durability test for alkali-silica reaction. Alkali-silica reaction occurs between reactive silica in your aggregates with the pore solution in concrete. Pore solution in concrete has a pH of, say, 13 or so. It's very alkaline. And at that range, you can have a reaction between those alkalis and silica, which is usually your fine aggregate, is silica-based, and you'll form an expansive gel. You'll get great, very high cracking with that. So you want to avoid, of course, alkali-silica reaction in your concrete. So testing our aggregates, we see that our dolomite, which is our virgin coarse aggregate, was pretty much non-reactive, just 0% expansion with time. You store these, make these mortar bars, and you store them in sodium hydroxide solution. So you're constantly supplying alkalis for this reaction. And so we can see that dolomite was non-reactive. This was the FRAP, which after we removed the binder, we tested it. and that was also a dolomite aggregate, so non-reactive. The frap fines themselves expanded a little bit more, probably just from the asphalt swelling. And then the sand, which consisted of quartz, which is silica, quartz and dolomite sand. We can see that it was a little bit above the limit. This is IDOT's limit for expansion. So pretty much with this scenario, with a slightly expansive sand, non-reactive coarse aggregate, it meets group 2 by IDOT, which pretty much says as long as the mix contains slag or fly ash or use a low alkali cement, ASR should not be an issue. So in the end, the big conclusion here is that frap is not an issue with ASR, provided that it's a non-reactive aggregate base like dolomite. Now coming to fracture properties tests we did. We did a single-edged notched beam using the 2-part fracture model by Jenkins Shaw, which I believe a pretty well-known test setup and study here. So pretty much all it is we have a long, thin beam. We cut a notch of 50 millimeters over the 150 millimeter depth, and then we load it from the top, and we measure the, as we'll see here, you load it from the top, and you have a clip gauge at the bottom measuring the crack mouth opening displacement. So pretty much with these fracture properties, we found a decrease in the peak load, which was expected based on our strength results we found. So reduction in peak load with increasing frap. Also a slight decrease in the fracture toughness, K1C, with increasing frap. The critical crack tip opening displacement was relatively unaffected here, looks like. And then looking at our initial fracture energy, relatively unaffected by our frap content. And then if we look at our total fracture energy, the total work of fracture, somewhat unaffected. It may be a little bit higher at higher frap contents. Probably warrants further study to confirm this. But relatively, we concluded the fracture properties were unchanged by adding frap, which is a very important concept considering we have a reduction in strength and yet our fracture properties are unaffected. So that might actually tell us that when we test a slab, that we may have similar properties between the virgin aggregate and the frap aggregate concrete. Now we also tested a secondary frap source, which we called dirty frap, and I'll get into that why we call it dirty frap. Pretty much, let's go to the gradation first. Pretty much it was a finer graded aggregate as we look at the gradation. The red line is our normal frap that we used in the previous slides, the previous mix design. And then this is our dirty frap, the blue line. So we can see it's a much higher content passing the number 4, which is why we call it dirty. It was an unwashed source, so there were a lot of fines. You can just see this is the normal frap we used, and this is the dirty frap. You can see a lot more kind of smaller particles, also higher asphalt content. We had a 3.3% asphalt with this dirty frap, 2.1 with the typical frap we used. And then what we did is in the lab we sieved to get rid of the fines, and we also washed it to try and get rid of the fines, which is what we see here on the gradation plot. This green line is after washing or dry sieving it. We get rid of a lot of those fines passing the number 4. So we wanted to see what was the effect of getting rid of these fines. Was it critical that we get rid of these fines? And pretty much what we found is it's not an issue to remove the fines. If we keep the dirty frap as is with the fines, we can see that it's higher than after we washed it and sieved it. So really we kind of concluded that we shouldn't remove those fines, so maybe. IDOT requirement of 3,500 PSI at 14 days again. We can see that all of our mixes passed, even at 50%. This is compressive strength at 28 days. We have an increase in strength as expected. Same with split tensile strength. It's consistent with our previous findings that the split tensile strength will decrease with added frap. Also, we can see that the washed and sieved, after we remove those fines, reduce the strength even more. So really, we should just probably keep the fines in there. So overall conclusions, we found that you can use probably 50% FRAP in your concrete mix without having too much of an effect on the strength and durability properties. Definitely there's a reduction in strength, but durability we found to be relatively the same even though we added FRAP. 50% can meet IDOT's strength requirements for compression and flexural strength. For the most part, we found shrinkage was unaffected, and also with the restrained shrinkage, the strains were slightly greater with the control mix, and we may have higher stress relaxation capability with using FRAP. Also looking at the chloride penetration, relatively unaffected, not much change. We had good freeze-thaw durability by using FRAP. ASR, there is not an issue with the FRAP, and our fracture tests revealed that we may have a higher fracture toughness, but relatively the same fracture energy. And with that, I'd like to bring up, we're doing slab testing. We will be creating slabs probably sometime in the next few weeks here. If anyone's interested in helping us cast some slabs, we could certainly use your help. Pretty much what we're doing is we're testing this two-lift design that that's being used by the Austrians and also what was used at the Kansas DOT study. Two-lift is also what the tollway is going to be using on their test bed project this summer. So we'll be casting some 4-inch bottom lift with recycled aggregate, topped with a 2-inch virgin aggregate. So please see me if you're willing to help out with that. And I'd like to thank you for your time. If there's any questions, I'd be glad to answer them.
Questions?
No questions? Yes.
I'm really interested in the fluoride filtration test.
Mm-hmm.
Does that test really measure the permeability or the diffusivity?
No, the test does not directly measure the diffusivity of the concrete. It gives you an indication of what the diffusivity will be just by how high, how much charge passes between those two cells. So when you have a high amount of charge passed, means you have a pretty interconnected pore structure, so you can have chloride ions easily penetrate, or you can also probably correlate that to water permeability or air permeability. It's a lot easier for some sort of media or ion to pass through your structure. So you want a low penetrability on that test. But no, we're not directly measuring diffusivity.
What about the use of this for higher RAP contents?
Higher RAP contents, we probably certainly could investigate. The majority of studies in the literature search did use higher contents, say up to 100% coarse RAP replacement, also fine RAP they looked at. I would be kind of skeptical right now with the current state of the FRAP, putting it in the concrete. Certainly we'll be looking at bond improvement studies to try and increase the amount of FRAP we'll add to the concrete. Because of course, if we add more FRAP, we have a much better economy. We're having a more sustainable concrete, more economical concrete. So we want to use more FRAP or more RAP. But as of right now, with the RAP state as it is, I would probably limit it to 50%. Yes?
Your conclusions are valid as long as you use a ternary blend concrete like the one that you used, right? So how common is that agencies or contractors use this kind of concrete?
Ternary mixes right now are on an IDOT special provision. IDOT will allow them, but the contractor has to say, you know, I want to use a ternary mix. Typically, you're only using a binary mix, using just, say, slag or just fly ash. Ternary mixes, the tollway is going to be using a lot of ternary mixes. They're very interested in ternary mixes just because of the economy to it. You actually, in the end, you get a much better microstructure by using slag and fly ash. I know Indiana DOT is using ternary mixes, not with slag. They're using silica fume and fly ash on their bridge deck mixes. So they're starting to become more popular, but still I think a lot of people prefer to use binary mixes.
Would you expect the conclusions to differ, though, if you just use straight cement?
Absolutely. Absolutely. I would probably say that the permeability would be higher. The chloride ion penetration test would give you higher results, because in using slag and fly ash, we really densified the microstructure. I can get into the cement chemistry, but you guys probably may not be interested in that. But in the end, if you use slag and fly ash at a later age, which is when we tested it at 56 days, you will have a denser microstructure, and typically a stronger concrete at later ages. At early ages, by using a ternary blend, you may have lower strengths than a straight cement mix, but the late gain is much better than plain cement.
But do you suspect using straight cement we could still use RAP?
You can, sure. Maybe not as high as 50%. The only way to know that would be to run tests and see what happens. But yeah, you probably could. I would say maybe 35% FRAP replacement if you use straight cement would probably work just fine. Yeah.
It was a very nice presentation, thanks.
Thank you.
But one thing I noticed, none of the material properties was not really compromised except modules. And you've shown some results at 21C, and almost half of the modulus reduction as you go to 50% rep. I'd assume this reduction would be even higher if you go higher temperatures. You said you would study creep in the
Yes.
next. So do you conclude that from this, for example, modulus, at least results, deflection problem will be the most critical criteria for using rep in slabs?
That's a good question. Yeah, you probably will have a lot higher deflection in the mix. You'd mentioned temperature dependency. We did not find a temperature dependency.
The modulus values.
Right. So we tested at 4, 21, and 54 Celsius. I believe the difference in modulus between 4 and 54 was only 7% difference in modulus. So really it was not a big difference in modulus. And that was for the 50% mix. For the 0% mix, the temperature dependency, I believe, was only a 4% difference in modulus in that temperature range.
So within, let's say, one temperature set,
Yeah.
your reduction is almost, almost
it's a pretty significant reduction in dynamic modulus. It's not as high as a reduction in elastic modulus, probably I think only 35%. But yes, dynamic modulus, we have a significant reduction.
And this will be even higher if you use, let's say, dirty wrap, as you mentioned, and because if you keep the fine in there, which has a lot higher asphalt content,
Yeah.
this reduction would be even higher, then you will see even more temperature susceptibility in that case.
Probably.
Yeah.
Probably.
Actually, we looked into that, and that's not true.
But we didn't look into the dynamic modulus.
Yeah, we did.
Only with
At minus
these.
15 Celsius.
Minus 15,
But
you won't
not
probably
with
see the
30
effect
for
at minus 15.
With that?
You won't see the effect at minus 15.
Oh, I see what you're saying.
Yeah. I mean, if you test,
Yeah.
let's say, dirty rep at 21 with 3.3% asphalt content in the fines especially, because the most of the fines are carried by the finer portion of your rep. The coarser portion
Yeah.
doesn't carry that much asphalt content,
Right.
so the finer carries the even higher percentages of fine. So this temperature susceptibility will be higher, so your reduction
Probably.
can be even more than 50% in that case.
Yeah, that's certainly something to investigate, and that probably would be the case. But like I said, it's probably only something I'd have to look at. But I agree with
You
you.
already reported something from the literature. You mentioned about the slab deflection faulting problem in one of your
Oh, that
cases,
was
and it was a little bit higher.
Yeah, that was the Kansas DOT's
Yeah.
study.
Very small.
But it was a very small faulting, despite the concrete being over 10 years old. It was a pretty low faulting. Here it is. Yeah, the faulting was 0.22 millimeters per joint versus the control at 0.15. Yeah, there was a difference in faulting, but these are also different mixes. You know, this is for the 2-lift mix. This is for just a straight, plain 12 inches concrete slab, single monolithic slab. So of course there's going to be a difference with that too, I would feel. But really I don't expect there'd be too big of a difference. Of course when we do our slab testing, we'll definitely see what the difference is, because we will have 2-lift versus full depth mixes to test. And we'll definitely see what the effect of that is. And for the slabs, we are using a dirtier frap. We'll have a higher fines content when we do our slabs.
Yeah, I'd like to make a comment though, because we looked into your questions because it was puzzling that we didn't see any viscoelastic behavior. And most of the literature where there is, you have 100% frap and very low cement content. So it's like used as a base material. And people have reported that there is a very temperature frequency dependency when you use 100% frap plus low cement content. You're really, the aggregate then starting to dominate the behavior. But our suspicion is that with a fair amount of cement, you see less of, we don't see an effect on the film thickness yet with the mixes we've tested. But you see an effect of the modulus. And I think that's why we focused on the fact that probably dirty frap and wash frap don't produce actually different results. Because it's a bonding issue, and if you have no bond for either one of them, then it doesn't really affect they affect the modulus the same way. The last comment briefly was with the lower modulus, it actually is beneficial because you don't generate as much stress. And that's why the shrinkage stresses effectively are reduced with frap, so it's actually a good thing. We actually get some benefits out of the frap that we normally don't see in concrete.
With regard to that, there was a study from Florida that did a finite element analysis similar to our program, ILLISLAB. They had their version, and their conclusion from that was due to the lower modulus, it was lower cracking susceptibility that they found. So, like I said, with slab tests, we'll know a lot more. Yes?
Were there any bonding issues? I mean, do you think cement will bond better with virgin aggregate than?
Yes. That is certainly an issue. I have samples here if anyone's interested in looking at that. You can really kind of see how that bond is affected. This image will tell us a little bit, but pretty much you can see this is from the split tensile. It just cracks right down the middle. And you can see there's a few, here's your virgin aggregate, and it's cracked right through. Here's one of the frap particles you can see on either side with a very thin asphalt coating. Those particles fracture through. But if you look at some of these, what I'm thinking are either agglomerated particles of sand and asphalt, or there's actually an aggregate in there, and that's just the film that cracked through. So it really does look like there is a bond issue here. And that is something that I'll be looking into for my PhD, is seeing if we can do anything to help this bond issue and improve this bond.
And maybe that how this decrease in modulus is due to this bond reduction or due to the viscoelastic properties that maybe also.
Well, the bond issue certainly is an option. It could just be that, say you have your cement matrix and the interface with the frap, it's just slipping. So you have a reduction in modulus in that way. That, or the other option is that the asphalt's compressible. So it's not a rigid body anymore, so you have a lower modulus that way just because you're compressing that lower modulus asphalt. So those are what we're thinking are the options for the reduction in modulus. And again, with the bond improvement studies, we'll certainly see how that's affected.
Okay. Thanks, Alex.
And please, if anyone is interested in helping with the slab tests, we need more help.